This week we're going to focus on one of the most important data structure problems in computational geometry. The importance of this problem is basically at the same level as a search tree or a binary search problem or a predecessor problem as in data structure and in one dimensions. And essentially you can think of it as a generalization of the search problem into two dimensions. So here's the input. We have a planar subdivision with n segment, which means that the input is a set of n disjoint line segments that divide a plane into some regions. For example, something like this. So this could be a map of a country or a bunch of regions, and you can think of every region is bounded by a bunch of line segments that in total we have n of them. We want to pre-process this. We want to store this in a data structure such that given a query point in the plane, we can find the region that this query lies inside. And if you think about this is in fact a generalization of a one-dimensional problem, because imagine that you have a bunch of values. So let's say this is the real line, and you've stored these values in a binary search structure, in a search structure. Given a query point, a query value, you can find the predecessor and successor of this value using a binary search tree. But this is equivalent to finding the interval that contains this query point. So in other words, you can think of a binary search problem as a data structure. You can think of the binary search tree as a data structure that solves a one-dimensional point location problem. Here, these intervals are the regions, and these vertices are the input values, and the binary search tree does the point location for us. There's a way, in fact, to achieve this solution in 2D that essentially matches the same asymptotic bounds that we have in 1D. So we can get linear space log n query time and log n preprocessing. This is quite impressive because when you think about this problem in 2D, it seems much more difficult compared to the one-dimensional problem. So therefore, it's very impressive that we can actually match the same bounds as we do in 1D. There is one way to get log n query time that is quite easy at the cost of increasing the space to n squared, and then we're going to try to improve this. So I'm just going to go over this basic solution. If you recall the solution for the line segment intersection, we had the sweep line. So now let's say we're sweeping a vertical line from left to right, and think of a moment in time when the sweep line is over here. Then the sweep line intersects these vertices, these sort of brownish vertices. And remember that we have stored these vertices, I meant line segments. So the sweep line is intersecting these line segments. Remember that we have stored these line segments in a data structure that is essentially a search structure that we can do some kind of search on them, because this is below, this is the lowest line segment, and etc. So we can do some searches on them. So therefore, imagine that the query point by chance is on the sweep line. In other words, we're looking at the moment in time when the sweep line is at the position of a query. If we had stored these line segments in a search structure, then we could do just a normal binary search. In log n time, we could find this line segment that is above the query, and assuming that these are stored in a doubly connected edge list, using the face pointer of this line segment, we could find the face that contains the query point. So therefore, it is sufficient to find this segment above, which is the same as a 1D search structure. Unfortunately, we have n event points. In other words, these set of line segments that intersect the sweep line changes all the time. This could change up to n times. Remember that these are disjoint, so therefore we don't have an intersection. So we have 2 times n event points in the maximum. But at every event point, we could have a different set of line segments intersecting the sweep line. If we store each one of those sets in a normal one-dimensional search structure, in total that would take n squared space. The idea that we're going to explore in the remaining videos is that we can remember this structure for later use, but we would remember them cheaply, in a sense that in total, all these n different data structures could use linear space instead of n squared space.